We're continuing with 9.7 to 9.10. Uh, review number 4. This is the third page here, number 7. Find the Maclaurin series for the function, so the first 4 terms and the general rule. So we need to know what the Maclaurin series for cosine of x is. So we can build the cosine of x to 3/2 starting with cosine of x. So cosine of x is 1 minus x squared over 2 factorial. Each term will be alternating in signs, but the degrees for all the exponents will be even powers. So this is x to the 0 power, x squared, x fourth, x sixth, and then the denominator, the constant coefficient, will be the same as the exponent values. So the way we write the general term, -1 to the n to represent the alternator, and then x to the 2n over 2n factorial. The exponent and the factorial will match and will always be even values. So if we want to build cosine of x to 3/2, then all we do is we can replace every x we see with 3/2, including the x in the general rule. So if we want to rewrite the general rule, we can just replace x with x to the 3/2, and if we clean this up, we get x to the 3n, because the 2 in the denominator, 2 in the numerator will cancel out, x to the 3n. And then we can either from here build the first 4 terms, or we can plug x to the 3/2 in and individually do that. Either way, we're going to get x to the 3 over 2 factorial as the second term. Then x to the 6th, when we plug in 2, we'll get 2 times 3, which is 6. 2 times 2, which is 4 factorial. And then if we plug in 3 times 3 is 9. 3 times 2 is 6, 6 factorial. Okay, so there we have Maclaurin series and the general rule for this new series. Okay, part B, we have 2 sine of x cubed. So again, we're going to identify the parent Maclaurin series, which is sine of x. So sine of x, it's the pattern for sine of x is going to be odd exponent powers. So first power, third, fifth, seventh, and then the denominator factorial will match the exponent up top. So the way we create odd numbers is we start off with an even number, such as 2n, and then we either add or subtract 1. In this case, the rule, this rule is to add 1. So if we start with 0, we're going to get x. And if we plug in 1, we'll get x. If I plug in 1, 2 times 1 is 2, plus 1 is 3. And so that gives me that odd exponent. And we just go down the line there. So this is the Maclaurin series for the parent graph sine. And then here's the general term, general rule. From here, we can build the sine of x cubed. We can build one term at a time. So let's replace each x in the general term with x to the x cubed. So if I do x cubed, I can clean this up to be x to the 6n plus 3. So this is my general term, general rule. And then from the general rule, we can build our first 4 terms of the Maclaurin series. So I need to make sure I multiply 2 through each of the terms, and then go through these steps here. So like if I plug in 0, I'll get x to the 0 plus 3, which is x cubed, x cubed times 2. And we go down the line. If I plug in 1 in for the n values, I'll get 2x to the 9th over 3 factorial. And if I plug in 3, that's my third term, and then my fourth term, 21. Okay, part C, e to the 3x plus e to the negative 3x. So we can identify the parent Maclaurin series, which is e to the x, which is 1 plus x squared over 2 factorial, x cubed over 3 factorial. From here, we can build our next term. So e to the 3x, replace every x we see from e to the x with 3x. And then here we have our first 4 terms, first few terms of e to the 3x. E to the negative 3x, I can replace every x we see with negative 3x. Okay. And then notice that if I'm trying to add these 2 terms together, notice that every other term will just nicely cancel out. But so either the terms will double or they're going to cancel out. So the first term will double, second term will cancel out because we have 3x minus 3x. Third term will double because we have the same two terms added together. Fourth term will cancel out. So really, we can just do 2 plus, and then we can double 3x quantity squared, and then double 3x quantity to the fourth, so on and so forth. And then if we look at this, we can kind of create our general term, which is the fact that 3x is always going to get raised to powers of 2, or factors of 2. So 2n will represent that pattern. And then the denominator will always match the exponent that we see, so 2n factorial. Okay. And then the 2 is being multiplied through because every term is going to get doubled, so that's why the 2 is there. Okay. Part D, cosine of 4x over 3 root x. So we can build this piece by piece. First, we can see we're going to build from the cosine of x first. So cosine of x, we have the first 4 terms here. Cosine of 4x, all we do is we can replace every x we see with 4x. And then we can divide each term also by 3 root x. So I'll divide each term by 3 root x. And then it's just a matter of doing guess and check, trial and error to create something, a general rule that is appropriate for the terms that we found. So I can see that everything is being multiplied by 1/3, so that's where that 1/3 comes from. There is a factorial of 2n factorial that we see here, because we see 2, 4 factorial, 6 factorial. And in the numerator, we have 4x quantity squared, or raised to 2n. Now, x is also in that sense, but if we combine the x together, the x is also being raised to 2n, but then we also have to account for the fact there's always a root x. So we can say 2n minus 1/2 will then allow for the combination between the x in the numerator and the x in the denominator. So x, in this case, x to the 6th minus x to the 1/2, or x to the 6 minus 1/2, the same thing as x to the 6th over square root of 6. So that's where the negative 1/2 comes from. Okay, let's go to the last page here. Okay, which of the following is the coefficient of x to the 4th in the Maclaurin polynomial generated by cosine of 3x? So we can build our cosine of 3x. So here's the first term. Second term, the derivative for cosine of u is negative sine of u times u prime, and then becomes cosine of u times u prime. So that's why we're always multiplying by factors of 3. So here is the fourth term, x to the 4th. We'll go with the fourth derivative here. The fourth derivative, the derivative for sine of u is cosine of u times u prime, so we get to the fourth derivative. But this is not asking for simply for the fourth derivative evaluated at 0. It's asking for the coefficient. So we also have to account for the 4 factorial in the denominator, okay? Because this is the fourth derivative evaluated at 0 over n factorial. In this case, my n is 4. And then x minus 0 to the 4. So this entire expression is my coefficient. So the fourth derivative evaluated at 0 is simply going to be 1. This whole thing will become cosine of 0 is 1. So 3 to the 4th over 4 factorial is 81 over 24, which is 27 over 8. Find the coefficient of x to the 68th in the Maclaurin polynomial generated by cosine of 3x. So 68th degree, notice that this goes through a series of variations for derivatives, and it's going to start repeating after it hits the fourth derivative. So basically, if we want to figure out where 68 lands on, we can just divide 68 by 4 and then look for the remainder. The remainder will tell us which of these variations, which derivative variation 68 will land on. So if we do 68 divided by 4, we get 17, remainder 0, and so it will land as a variation of cosine of 3x. But notice that coefficient is always being increased by factors of 3, so therefore 68 would be 3 to the 68th, okay, over 68 factorial, and that's my coefficient. Okay. All right, number 9 and 10 says find the Taylor polynomial of degree n centered at C for the below. So we start off, we want to build our Taylor polynomial. So natural log of x, we're going to work our way down to the fifth derivative. And the derivative for ln of x is 1 over x, or x to the negative 1. And then from here, I can just keep on applying power rule. And then once I find the derivatives all the way down to the fifth derivative, I'm going to evaluate each derivative at the center at 1. So if I plug 1 into each of these derivatives, here are the values I'll get in return. And then if I want to build the fifth degree polynomial, I'm going to start off with my with the tangent line equation. So it's just going to be y sub 1 minus plus the slope, which is 1 times x minus 1. Right, that's the center. And then I'm going to start building my each of the derivatives. So the second derivative evaluated at 1 over 2 factorial x minus 1 squared, and then 2 over 3 factorial x minus 1 cubed, and then I just go down the line. Okay. All right, part B. Same idea, except now I'm trying to find the derivative starting with 1 over x. So we find each of the derivatives, evaluate each of them at the center, which is at 1, and then we can build our Taylor polynomial centered at 1. Notice these are all each of the respective derivatives divided by n factorial. So then it's just a matter of trying to clean up these coefficients, and then finally we have our cleaned up, simplified polynomial, Taylor polynomial in the fifth degree.